In this lesson, we'll learn how to use the information we know about graphing transformations of functions in order to graph functions or quadratic functions that are in a different form than the transformation form. In other words, if we are given a quadratic function that's a trinomial, how can we convert that into transformation form so that we'll be able to apply those shifts? So we're going to start by just graphing a few functions, applying some transformations to our basic graph of f of x equals x squared. So let's start off with what happens when we graph 3x squared, or g of x equals 3x squared. So remember that what that's going to do is it's going to multiply each of our outputs by 3, therefore stretching the graph vertically by taking each point on my graph and stretching it 3 times as much, which is why we end up getting a graph that looks a bit thinner. So what if we were to now take another transformation by taking the graph of 3x squared and now applying the transformation of x plus 2 quantity squared? Notice that that would be a horizontal transformation, left 2 units. So we would take this green graph of 3x squared and just pick it up and move this base or this vertex left 2 units. But what if we were to now take one last step and take a look at this vertical shift, which moves me down 4 units? So we're going to take this graph, or the blue graph, and now just take 4 units away from all of the outputs, which is going to now take this vertex and move it down 4 units. So the thing we want to focus on now is that if we wanted to graph this function, this quadratic function, with these transformations where we have a vertical stretch, we have a left movement, and we have a movement downwards, that what that's going to do is it's going to make my vertex -2, -4, which should make sense if you think about this, that if you move from 0, 0, left 2 units, and down 4 units, that should take me to the point -2, -4. So if you have a function ax squared, we should realize that the value of a is going to cause the graph to either open upwards if a happens to be positive, and it'll cause the graph to open downwards if a happens to be negative. So for instance, if a is +2, that would be an upwards parabola. But if a was -2, then that would mean a reflection over the x-axis occurred, causing it to open downwards. Now, if you take a look at this vertex, when I now apply some sort of transformation to it, let's call that transformation x minus h, which would move it horizontally h units, and plus k, which would move it vertically k units, then notice that the vertex will now be located at the point hk, because of the fact that it moved somewhere else h units in one direction, let's say right, if h happened to be positive. But if h was negative, then that would mean that it moves left. And finally, k would cause the graph to move down k units. If it was a negative k or a positive k, that's what allows it to move in the vertical direction. So what this does is it now allows us to just look at our transformation form and determine what our vertex actually is. Now that we have the vertex, we can come up with another feature of a parabola that's referred to as the axis of symmetry. The axis of symmetry is nothing more than this imaginary line that goes straight through the vertex of the parabola, cutting it in half to where we could see that the same distance, or each point is the same distance on one side as it is on the other. And so if we know a point that's on one side of the axis of symmetry, we can use symmetry to know what the y coordinate is on the other side as well. So if we want to determine the vertex and axis of symmetry of a function that's already in this form, we just have to think about the fact that this graph moved right 3 units and down 1 unit. If I moved right 3 and down 1, that would cause the vertex to be at +3, -1. Now, the thing to recognize is that the vertex will always have an x coordinate that's the opposite direction or the opposite of the sign that we actually see here. When you take a look at the vertical shift, the K unit is actually referring to it being moving up or down. So if K is negative, that means it's moving down, and if K is positive, it's moving up. So it moves the same direction as the sign. Now, if you try to picture where 3, -1 is, that's on the right side of the y-axis. So our axis of symmetry is actually going to be over at the vertical line x equals 3. Now, it's important not to just say the axis of symmetry is 3, because an axis of symmetry is actually a vertical line that cuts through the graph at x equals 3. So this allows us to understand some important information about the graph of a function that's already in what we call vertex form, sometimes referred to as transformation form. Unfortunately, a lot of times we have a function that might actually be a trinomial. And so by looking at this trinomial, we know that it's going to be a parabola or a quadratic function because it's got a highest power of 2. But it doesn't look like the form that allows us to see whether it moves up, down, left, or right. So our goal here is to be able to complete the square in order to rewrite this in the form that we need it to be. So let's talk about the process of completing the square. Our goal is to start with a trinomial and turn it into a form like vertex form. So if we think about what happens here, we first of all want there to be a coefficient on the outside of parentheses. And we also want there to be some number added or subtracted to the end after the parentheses. So our first step is to take this positive 17 and make that the constant at the end, and then factor out a 2 from the first 2 terms. So what's in blue in this second equation here is exactly the same as the original function, except it's already starting to look a little more like vertex form. The only difference is we have to somehow get this x minus h quantity squared. So the goal in order to do this, or rather the method we would take here, is that we need to add some constant onto this -6x so that it's going to become factorable. And not only that it becomes factorable, that it could factor into the same factor twice, which is what x minus h quantity squared means. So we're going to add this special quantity that's half of the middle coefficient squared. So half of -6 is -3. So what we're going to do is add -3 squared inside of the parentheses. That's going to allow me to factor that new trinomial in parentheses. We have to realize that adding and subtracting the same quantity from one side of an equation will still make it an equivalent equation. So by adding this quantity in red, I've changed the equation by technically adding 18. Because -3 squared is 9, and if I were to distribute the 2 back into it, that means that I really have added an extra 18. So I've changed this original function, so to compensate for that, I have to subtract 18 from the very end of the function. We now can keep that 2 on the outside. And if I factor x squared minus 6x plus 9, that factors into x minus 3 times x minus 3. Or in other words, x minus 3 quantity squared. And now we can see that positive 17 minus the extra 18 is giving us -1. So we've used this process called completing the square to change from a quadratic trinomial into this vertex form. And because this is obviously the same function as the original function, just in a different form, we now have a way to convert it to a form that's going to allow us to graph. Now notice that this equation that we just got, this new function, is exactly the same as the example we did at the beginning of this slide, and therefore it's going to have the same vertex and the same axis of symmetry. So let's use what we've learned about finding the vertex and axis of symmetry to come up with a more accurate graph for the parabola negative x squared plus 2x plus 8. Now we want to find all of the important features of this graph, not only by transforming it and moving the vertex, but also finding a couple more important points, namely the x-intercepts and the y-intercept. So if we wanted to find the vertex, we can use a vertex formula in order to realize that the x-coordinate is -2, negative b, over 2 times a. And that gives us an answer of x equals 1. We can then plug in x equals 1 and realize that that is our axis of symmetry. When we plug 1 into the function and evaluate, we get -1 plus 2, which is 1, and 1 plus 8 gives me an answer of 9. Now, although this is one method that some students have learned in order to find the vertex by just using this formula, -b over 2a, we're going to go ahead and take a look at this from the perspective that we just learned about completing the square, so that we can actually get this to look like a transformation form and then use that as well. So remember, the first thing we want to do is separate off the plus 8 and factor out the coefficient in front of x squared from the first two terms. We're now going to add half of -2, which is -1 squared. So we basically have added 1, but because of the fact that distributing that negative would cause that to be -1, then what that really means is that we've technically subtracted 1 from the original function. So to compensate, we have to add 1 back on, which now gives me the vertex form, or the transformation form, of the negative quantity of x minus 1 squared plus 9. And that will also give me the same vertex that we found by using that formula. This is my preferred method because it actually also gives us a transformation form. So we now know that we can plot the vertex and we can plot the axis of symmetry. We also know, because a is negative, we know that it's going to open downwards. But we want to find now a couple more important pieces of information, namely the x-intercepts and y-intercept. So remember that in order to find x-intercepts, we set the function equal to 0 to find out where the y-coordinate is 0, and we now factor. So we're going to go ahead and factor out the -1 from each term so that it turns into a quadratic where the first term is positive. And now we can factor this into two binomials, namely x plus 2 times x minus 4. I encourage you to verify that by distributing back through and make sure that we get back to the original polynomial. But now that we've separated this into two factors, we can apply the zero product property by setting each factor equal to 0. And that gives me an x value of -2 and an x value of 4. So because those are the values that we found by setting the y equal to 0, that means that my x-intercepts are at -2, 0, and 4, 0, and therefore we can plot those on my x-axis. Now, one check to see that we're correct is that each of these is 3 units away from the axis of symmetry. 4 is 3 units away from 1 on the right side. -2 is 3 units away from 1 on the left side. And therefore, that's still coinciding with what we expect from a parabola. So to find our y-intercept, we simply set the function's x-coordinate equal to 0 by plugging in 0 to the function. Now, we could plug in 0 to the standard form that was given, or we could plug it into vertex form. Either way, we're going to get the y-coordinate of 8. So if the y-coordinate is 8 when the x-coordinate is 0, we simply have a y-intercept of 0, 8, and therefore we plot our y-intercept. So by doing all of this information, we could have just come up with a rough sketch by having a parabola shifted right 1 and up 9, opening downwards. But now we used our tools to be able to find even more important information, the intercepts, in order to graph. Now, the last step here, we typically want 5 points when plotting or before graphing a parabola. The vertex, the y-intercept, oftentimes 2 x-intercepts, And by the time we finish, we can use symmetry to find our fifth point. Connect the dots, and there's our parabola. So what we've seen now is how can we start with a quadratic trinomial and use the tools of completing the square to turn it into transformation form, and use our tools for setting x and y separately equal to 0 in order to find all of the important pieces for our function.